Swayam Prabha. Digital India. Educated India.
So, warm welcome to the 13th lecture on the subject of digital signal processing and its applications. In this lecture, we intend to introduce a new transform. But before we do that, we would like to ensure that we've understood the previous transform entirely, the discrete time Fourier transform, and therefore, I would like to allow a few questions, so that we clarify any doubts that might still be remnant before we proceed to discussing a new transform. So, we will take a few questions from the class. Are there any questions, doubts or difficulties? I may mention that we also have a course Moodle page. One should make use of the technical discussion forum there to discuss concepts. Yes. So, any doubts or difficulties so far? No, not at all. So, the question is, what can we say about the discrete time Fourier transform? What can we say about the DTFT of UN? The sequence UN is very important in discrete time signal processing. It is a sequence which is 1 for n not equal to 0, in fact for n greater than or equal to 0, and 0 for n less than 0. So, essentially it is 1 for the entire positive set of integers n, positive and 0 and positive integers, and so it is called a unit step because it looks like that, it looks like a unit step. So, it looks like a unit step. Now, this unit step function is a very important function in discrete time signal processing. One importance is that when you multiply the unit step by any function, it retains the positive side of samples and destroys the negative side, right. So, it is useful in concept. It is also useful in describing what is called the accumulator system. So, an accumulator system, as the name suggests, accumulates the inputs. So, it keeps taking the sum of what it already has with the current input. So, if you consider this system, and if you take the LSI system described by this equation, where the output at a current time is equal to the output at the previous time plus the input at the current time. So, what it does is it keeps accumulating, whatever is coming now, it accumulates in itself. So, it keeps taking a sum until that point in time. This is called an accumulator system. Now, if we treat it, in fact, this can be looked upon as an LSI system if you treat the accumulator as having operated all the way from minus infinity, right. And the impulse response of this LSI system is UN, that is easily seen. Because if you have an impulse, then if the impulse is given to an accumulator, the output is 1 starting from 0 onwards. The question is, one way to ask the question is, would the accumulator have a frequency response? That is another way to reframe the same question. The answer strictly is no. That is because if you look at the discrete time Fourier transform of the so called DTFT, I mean that does not exist really, DTFT of UN, it would be summation n going from 0 to infinity e raised to the power minus j omega n, which is actually divergent because the common ratio, it is a geometric progression with common ratio equal to e raised to the power minus j omega. And the modulus of this common ratio is 1. So, such a geometric progression is known to be divergent. However, some people like to write this as the sum 1 by 1 minus e raised to the power, some people write it. And say it should be accepted except for omega equal to 0. Some people like to write that. That is not entirely correct. Actually, this is divergent. However, I mean, the way to interpret this is that if you happen to give the accumulator an input other than un, so among the complex exponentials, if you happen to give the accumulator a complex exponential input other than un, you could possibly hope for a non-unbounded or a bounded output. That is the interesting part. So, although this system, if you look at the LSI system, its impulse response is not absolutely summable. So, it is very clear that the system is unstable, Bibo unstable. But then, it exhibits an unbounded input for some selected bounded outputs. I am sorry, it exhibits an unbounded output for some selected bounded inputs. So, it is not, unlike some other systems that we will soon see, this system is selective in its instability. So, some people like to call it marginally stable or marginally unstable. Of course, these are all informal terms, they have no real formal meaning, right. Otherwise, the system is unstable. Strictly speaking, it does not have a frequency response in the true sense. But the question whether it produces an unbounded output for every bounded input has the answer no. It does produce bounded outputs for several bounded inputs, including some of the complex exponentials, but which needs to be seen carefully, all right. In particular, when you take un itself, if un is given as the input to the system, the output is unbounded clearly. So, if you give a constant zero frequency input, so to speak, it has an unbounded output. But if you give it, for example, the highest possible frequency that you can see in discrete time, where you alternate 1 minus 1, 1 minus 1, omega equal to pi, there actually the output is not unbounded. The output is bounded by 1. But the output is divergent still, right. So, these are the subtle points. So, in that sense, the frequency response does not exist. Anyway, so one should not really say that it has a DTFT, it does not. All right, any other questions? All right, so if there are no other questions, we will then take this very example further. In fact, it was good that this question was asked, because it leads us to the next limitation of the discrete time Fourier transform. The discrete time Fourier transform, as you see, does not exist for all sequences. In fact, the discrete time Fourier transform exists when the summation corresponding to the discrete time Fourier transform converges. What if the summation does not converge? Obviously, it does not exist. So, then what do we do? Do we have some other transform domain where we can study the same sequence? Or do we have to make do with natural domain studies or natural domain processing? It turns out that we do have a more general transform which allows us to deal with sequences which are not absolutely summable as well. Let us take an example. So, let us take a more troublesome sequence. I say more troublesome because as we said, the UN sequence, the unit step sequence, at least does not produce an unbounded output for all bounded inputs. But the sequence that we will soon see, if it becomes the impulse response of an LSI system, it more or less always wishes to produce an unbounded output, except for some very chosen bounded inputs. That is the interesting thing. In its the system is, so there are, instability also has different grades. The accumulator is an unstable system, but unstable, it's like saying the person is insane, but there are only certain points or certain situations where he exhibits insanity. But here you have a system which normally behaves insanely. It is very rarely that the system exhibits sanity, and that system is, let an LSI system have the following impulse response. Hn is 2 raised to the power of n un. Now this LSI system would at the slightest provocation exhibit an unbounded output. In fact, it is very clear that this impulse response is not absolutely summable, so it is an unstable system. And you see, I mean, when you have an unstable system, what do? You want to study its frequency response. Now, I liken the frequency response of a system to the behavior under training. So, when you give a complex exponential, what does it do? You have trained the system and I would like then to take an analogy. Here, you could think of a system like this, like a ferocious tiger, and a system where the DTFT converges, maybe even un perhaps at the extreme, or definitely half raised to the power of n un, like a little dog. Now, it is not too difficult to train a dog. You can just hold a dog in open space and open, in front of you, and slowly by using rewards train it. On the other hand, trying to train a ferocious tiger is dangerous both for the trainer and for people around. Is that right? And therefore, the only way to train a ferocious tiger is to encapsulate the tiger in a cage, and then of course use rewards or punishments to train. Now, this system that we have here is like a tiger, and we need to encapsulate such systems first in a safe cage and then train it. Train it means see what happens when you give it specific inputs. How do we encapsulate the tiger in a cage? We encapsulate the tiger in a cage by multiplying it. What is a cage? A cage is stronger than the tiger. So, we encapsulate the tiger in a cage by forcing an even more troublesome sequence on that system. So, multiply Hn by r raised to the power minus n. R is a number greater than 0. So, for example, here if you happen to multiply this sequence by any such exponential where r is greater than 2, it would get encapsulated, isn't it? Here r greater than 2 would encapsulate the tiger. And now you can, of course, you can take the DTFT. So, we can take the DTFT of H, the encapsulated tiger. You can train the encapsulated tiger. That is obvious. For example, take r equal to 2.5. Then Hn r raised to the power minus n would certainly be, the DTFT of that sequence exists. Now, you see, that is what we are now going to do in our effort to deal with such unstable systems. We are going to encapsulate, we are going to first capture their naughty behavior, and therefore, instead of multiplying by e raised to the power j omega n, we multiply. So, sequences like this, you see, sequences like this need to be multiplied by r raised to the power of n or minus n, e raised to the power minus j omega n, and then summed. R is like a radius and e raised to the power j. So, r e raised to the power j omega is the complex number that we are talking about here. And now you know the role played by r and e raised to the power j omega. Put z equal to r e raised to the power j omega. So, essentially we are saying consider summation n going from minus to plus infinity x n z raised to the power minus n. We call this the z transform of x n. And we denote it by capital X of z for obvious reasons. So, of course, a z transform, unlike the discrete time Fourier transform, is a function of a complex variable. The discrete time Fourier transform was a function of a real variable omega. In fact, in a way there is a relationship between the z transform and the discrete time Fourier transform. If the z transform can be evaluated, if the z transform can be evaluated for r equal to 1, then that gives its DTFT. So, Z transform for r equal to 1 is the DTFT if that can be evaluated. It may not be possible to evaluate it, it may not converge, right. Let us take an example. Suppose we take this tiger once again. Two raised to the power of n u n. Of course, we need r to be greater than 2. So, the DTFT cannot be evaluated. DTFT does not exist because r equal to 1 not allowed. But of course, we can always take another example. H n is half raised to the power of n u n. And indeed, in this case, r needs to be greater than half. So, r equal to 1 is allowed, and therefore, the DTFT exists. In fact, capital H of z, which is summation n going from 0 to infinity half raised to the power of n z raised to the power minus n, which is the z transform of H n, can be evaluated for r equal to 1, right. So, this is the z transform and this can be evaluated. In general, of course, H z here happens to be 1 plus half z inverse plus half squared z to the power minus 2 and so on. It is a geometric progression with common ratio half z inverse. And therefore, the sum is of course easy to evaluate. Now, obviously the GP converges if mod half z inverse is less than 1, which means mod z is greater than half, or it is the same thing as saying r is greater than half. Mod z is equal to r by definition. So, we have mod z is equal to r. So, we need r to be greater than half, and of course, this h z can be written as 1 by 1 minus half z inverse mod z greater than half. Notice a Z transform always has an expression and a region of convergence. A Z transform is incomplete without any of these two. I shall shortly illustrate that if we did not specify the region of convergence here, there would be an ambiguity in the sequence. Now, what can we say about the region of convergence? The region of convergence has nothing to do with omega. It has only to do with R. So, the region of convergence has always to do with circles centered at the origin. What is R? R is the radial distance of the complex number from the origin. So, the convergence or non-convergence of a Z transform has only to do with the radial distance of the points that you are considering from the origin of the Z plane. And therefore, the regions of convergence of the Z transform are always essentially between concentric circles with the centers located at the origin. That is a very important observation. Regions of convergence of the Z transform are always between concentric circles located with centers located at the origin. So, essentially a function of R, not of omega. Now, it should be noted that one of these circles could go all the way up to infinite radius, and one of the circles can go all the way down to 0 radius. So, the circles do not need to have non-zero radius or finite radius. Also, it is a moot point whether the circles themselves are a part of the region of convergence. The circles that bound the region of convergence may or may not be a part of the region of convergence. That needs to be seen case by case. This is particularly a tricky point when you are considering infinite radius and 0 radius. There is an issue there. Let us take an example. Let us take the sequence h n is equal to delta n. The simplest possible sequence that we can conceive of, the unit impulse sequence. The Z transform of this sequence is very easy to see. It is essentially 1 into z raised to the power minus 0, which is 1. And this holds true for all z. And therefore, the bounding circles have 0 and infinite radius. Essentially, the region of convergence lies between the concentric circles of radius 0 and radius plus infinity. The entire Z plane is the region of convergence here. However, in this case, the two boundaries are also a part of the region of convergence. The circle of radius 0 and the circle of radius infinity are parts of the region of convergence. Now, let us take the sequence h n is delta n minus 1. It is very easy to see that the Z transform is Z inverse, and it holds true for all Z, but Z equal to 0. Again, the region of convergence is bounded by circles of 0 and infinite radius. However, the circle of radius 0 is not included in the region of convergence, whereas a circle with radius infinity is. So, you see, it's a very tricky point. The bounding circles may or may not be in the region of convergence. That must be carefully seen. Again, let us take another such example. Let us take Hn is delta n plus 1, and it is very easy to see that the Z transform is simply Z, holds true for all Z except Z tending to infinity. So, the ROC is again bounded by circles with 0 and plus infinity radius. Very interesting. So, here we have all of the Z plane included, the same boundaries. The boundary Z equal to 0 or R equal to 0 is included in the region of convergence, but the boundary, the circle with infinite radius is not included. I must also draw the attention of the class to one difference between the notion of infinity for reals and infinity for complex numbers. The infinity in complex numbers is not a point or a set of points, it is a contour. In fact, it is several contours. Essentially, an ever enlarging contour takes you to the infinity on the complex plane. So, infinities on the complex plane are several ever enlarging contours. The circle is a possibility. As the circle enlarges and continues to enlarge, it takes you to the infinity on the complex plane. Any other contour, any other closed contour, as it expands indefinitely, takes you to an infinity in the complex plane. So, the notion of infinity in the complex plane is a little different, a little more general, a little more intricate than the notion of infinity on the reals, right. Anyway, so this is essentially about the region. So, you see the Z transform, now this of course illustrates that you have boundaries which are concentric circles, the boundaries need to be checked for inclusion or exclusion. But now we need to explain why it is important to specify the region of convergence along with an expression. Although sometimes we take that for granted, it is not correct to do so. One must always specify a region of convergence along with an expression. Let us take the very same sequence that we had, or let us take the very same Z transform that we had a minute ago. We had the Z transform 1 by 1 minus half Z inverse with mod Z greater than half. Now, here of course, it is very clear that Z equal to half, and that means mod Z equal to half can never be in the region of convergence here. That is because mod Z equal to half is a singularity, is a contour with a singularity. You see, at Z equal to half, this expression diverges, this expression has no meaning, the denominator becomes 0. That is called a point of singularity, where the expression is unevaluable. Now, you see, when a contour holds a singularity on it, then that contour cannot be in the region of convergence. A contour which hosts a singularity cannot be in the region of convergence. And therefore, we have only two possible regions. You see, the contour must be excluded. When there is a singularity on a contour in the expression, that contour cannot be in the region of convergence. So, the only choice is, as far as the region of convergence must be, you see, it must be what is called a simply connected region. You cannot have parts of it, you cannot have a region of convergence separate with some, part which is in no man's land. No. It must be a simply connected region. That means if you take any 2 points in that region, any contour joining the 2 points must all lie within the region. So, for example, in this case, it is very clear that we cannot allow the circle with radius half to be in the region of convergence. So, either you have the region of convergence within mod z equal to half or outside of mod z equal to half. And we have chosen the region of convergence outside mod z equal to half, but we could choose it within mod z equal to half too. So, let us see what happens if you take the region of convergence to be mod z is less than half. In that case, what we are essentially saying is we multiply the numerator and denominator by 2z. In fact, minus 2z if you please. And in fact, it is very clear that mod 2z is less than 1. Since mod 2z is less than 1, 1 by 1 minus 2z can be expanded using the idea of a geometric progression. One by 1 minus 2z can be expanded as 2z summation n going from 0 to infinity 2z to the power of n, as mod 2z is less than 1, by using the simple idea of a geometric progression. And we can write this out explicitly. So, we have 2 to the power 0 z to the power 0, so 1 plus 2z plus 2 squared z raised z squared plus and so on. And of course, we can now see hz too. Hz is very clearly minus 2z times this. So, it is minus 2z minus 2 squared z squared minus 2 cubed z cubed and so on and so forth. And it is very easy to see that this is essentially the z transform of the sequence Hn is equal to minus 2 raised to the power of n for n less than 0 strictly, and 0 for n greater than or equal to 0. In fact, I leave it to you to verify that this can be written as Hn is minus 2 raised to the power of n u minus n minus 1. I mean, the way we've arrived at that conclusion is that you have a summation here. You can identify z is the term, or z is contributed by the sample at n equal to minus 1. Z squared is contributed by the sample at n equal to minus 2 and minus 3 and so on and so forth. And of course, you can see there are no samples from 0 onwards. And of course, just as a matter in point, if you look at u minus n minus 1, u minus n minus 1 is expected to be 1 whenever minus n minus 1 is greater than or equal to 0, or n less than or equal to minus 1, isn't it? And 0 else, as we expect. Is that correct? So, the same expression 1 by 1 minus half z inverse, when associated with the region of convergence mod z greater than half leads to one sequence, and when associated with the region of convergence mod z less than half leads to another. Now, in fact, we can have even more complicated situations. We can have more than two possibilities for the region of convergence that we see later, and then we have more than two possible sequences if we do not specify the region of convergence properly. But we will come to that later. We will come to that, or we will see examples of that later when we look at a few more properties of the Z transform. Now, you see, let us look at the properties of the Z transform as we did for the discrete time Fourier transform. Let us first look at the linearity or otherwise. Now, in fact, it is almost trivial. It is almost trivial to show that the Z transform is linear. Or it is a linear operator. What I mean is, if you think of the Z transform as an operator which takes you from the set of sequences, and you know the Z transform is denoted this way, a script Z often. It is also sometimes denoted like this, script Z. Both of these are used as symbols for saying take the Z transform. If Hn leads you to Hz with an ROC RH, so you know you must always write it like this, an expression Hz with an ROC or region of convergence script RH. Script RH is a region between two concentric circles. Is that right? So, if Hn, and in fact now we use the same shorthand notation, if H1 and 2n respectively have the Z transforms H1, 2 with regions of convergence R H1, 2, then alpha times H1 plus beta times H2 would have the Z transform, or you can write Z transform alpha capital H1 plus beta capital H2. Now comes the question of region of convergence. What do you think we can say about the region of convergence? The region of convergence is at least the intersection of RH1 and RH2. It could be bigger. ROC at least RH1 intersection RH2. Could be bigger. This is often the case with the regions of convergence. The region of convergence is of course at least the intersection. It could expand beyond the intersection. And the expansion takes place because the trouble created by one sequence can be outdone by the other. Now, let us take an example. You see, let us take the sequence H1n is delta n plus half raised to the power of n un, and let H2n be minus half raised to the power of n un. It is very easy to see that, of course, H1n plus H2n has the region of convergence is, of course, you know, the Z transform is essentially the Z transform of delta n, and that is 1 for all Z, and the region of convergence is all Z. On the other hand, the region of convergence of either H1 or H2 is mod Z greater than half. So, here the intersection is mod Z greater than half, but the region of convergence has expanded beyond the intersection because the trouble created by one sequence has been outdone by the other. Is that right? So much so for the linearity of the Z transform. Now, we look at some other properties. What happens when we delay? Delay or shift, that is very easy. So, if xn has the Z transform, for variety let us use xn, we will use one of them in future, the Z transform xz with a region of convergence Rx. What is the Z transform of xn minus d? D is an integer. It is very easy to answer this question. We only need to write down the summation. The summation n going from minus to plus infinity x n minus d z raised to the power minus n, you see, can be evaluated by putting n minus d equal to m. Now, when n runs over all the integers, so does m for a fixed integer d, and therefore, this can be rewritten as summation m going from minus to plus infinity x m z raised to the power minus m plus d, and therefore, that is z raised to the power minus d x z. The only difficulty is what happens to the region of convergence. Now, the region of convergence is going to be affected by the factor z raised to the power minus d. So, the only effect that the factor z raised to the power minus d can have is to affect what happens at the boundaries. So, essentially it is almost RH as the region of convergence, possibly except boundaries. The region of convergence would almost be the same, but the boundaries have to be carefully seen. Let me give you an example, again a very simple example. Take delta n minus 2. Delta n minus 2 had the Z transform Z to the power minus 2. We have seen that before. The region of convergence is the entire Z plane excluding Z equal to 0. Advance this by 2. So, take n plus 2 in place of n there, and you get delta n. Now, the boundary also gets included. So, because of the multiplication by z raised to the power minus d, you need to worry about what is happening at the boundaries. Otherwise, the rest of the region of convergence is unaffected. The interior is unaffected. The boundaries could be affected. So much so for delaying or shifting. Now, we see a very interesting variant. We will see one variant of a property today, and then we will look at more properties in the next lecture. The important variant we will see is that of differentiation. And here we differentiate the Z transform. So, here we go the other way. Let xz be the Z transform of xn with a region of convergence Rx. We ask the question, what is it that has a Z transform dxz dz, or can we do something to figure out what happens to xn when we take the derivative with respect to z, if it exists. Let us write down the expression. So, dxz dz is dz times summation n going from minus to plus infinity xn z raised to the power minus n. Now, let us assume that this derivative exists. So, if it exists, then we can evaluate the derivative term by term. If it exists, then it is analytic. So, we see normally we expect, now we are going to consider, this is a subtle point. Functions in the complex plane can be analytic or not analytic in the region of convergence. Analytic means they have an infinite number of continuous derivatives. Now, we will initially deal only with Z transforms which are In fact, all through this course we will deal largely with Z transforms which are analytic in the region of convergence. So, in the region of convergence we have an infinite number of derivatives. Of course, one can always conceive of functions that do not have this property, but we shall not do it in this course. That is more of mathematical interest than practical. So, anyway, we can then take the derivative term by term, and that gives us minus n summation. See, it becomes summation n going from minus to plus infinity minus n times x n. Remember, x n is a constant with respect to z, minus n minus 1. And therefore, if you take minus z times dx z dz, that is summation n going from minus to plus infinity n x n times z raised to the power minus n. This is very interesting. So, what we are saying is that the Z transform of n times x n is essentially the derivative of the original Z transform of x n multiplied by minus z. Now, we have assumed the Z transform to be analytic in its region of convergence. So, all over the region of convergence, interior to the region of convergence, the derivative is valid. So, the region of convergence continues to exist at the derivative. I mean, so the derivative can spread all over the region of convergence. So, the region of convergence RH is definitely included here. Again, because of a multiplication by minus z, you need to worry about the boundary. So, the region of convergence is at least RH, if not more, at least the interior. Yeah, so, what we have said effectively is n times x n has the Z transform minus z dx z dz, and the region of convergence is definitely the interior of RH, if not more. And the more essentially refers to the boundaries. All right. So, this brings us to a very interesting point. In fact, we intentionally took this property before others, because this property can also be taken to the discrete time Fourier transform. If x n has a DTFT, we can ask what is the discrete time Fourier transform of n times x n. And in a way it can be answered by this property. If you can evaluate the Z transform on the unit circle means where r equal to 1, then you can evaluate, essentially you are saying the Z transform evaluated on the unit circle. The unit circle is a circle with a radius of 1 or r equal to 1. So, if you can evaluate the Z transform on the unit circle, then you can find out what is the Z transform, or what is the sequence whose Z transform is the derivative, right, multiplied by minus z, and that gives you the Z transform of n times x n. When you multiply a sequence by the time index, when you multiply a sequence by n, the effect in the Z domain is to take the derivative with respect to z and then multiply by minus z. These operations cannot be interchanged. You must first take the derivative with respect to z and then multiply by minus z. And in particular, if you do this on the unit circle, you get what happens to the discrete time Fourier transform. That is an interesting property. Now, we have to answer several other questions about the Z transform. The first question is, what happens when you convolve two sequences? The $1,000,000 question when you talk about linear shift invariant systems. So, when I want to see what happens to unstable systems when I give them inputs, I need to know what happens to Z transform under convolution. I also need to answer similar questions about the Z transform with respect to inversion. Can I invert the Z transform? Well, let me mention that it is most common to invert the Z transform by experience. That means we associate inverses for certain typical forms and we use those inverses to calculate the inverse of a more complicated Z transform. But anyway, in the next lecture, let us see a little more about some of these questions. Thank you.